In this video, I would like to examine, using the ideas of work and energy in Chapter 6, the situation you worked on in lab, where you hung a mass from the end of the elastic bands. I'd like to figure out two different things and ask a number of questions about the second thing. The first thing I'd like to figure out is, if you hung a particular mass from the end of an elastic band, how far would it go down before it came to rest, where it would hang in equilibrium? And then I'd like to figure out what would happen if, instead of letting the mass down slowly, you just let it fall down and watched it bounce up and down at the end of the rubber band. So to put some numbers to all of this, let's say that the mass that you're hanging from the end of the rubber band is 250 grams, which is around 250 milliliters of water, and that the spring constant, which is similar to what you found for the elastic bands, is around 0.5 newtons per centimeter. Let's just examine, first of all, what would happen if you let the mass down slowly and ask how far would the elastic band stretch before the mass would hang in equilibrium at the end of the elastic band. So I'm thinking of a situation like this. So the elastic band, I'll do my best to draw a spring here, initially is not stretched. Has a spring constant and the mass m here. And then you let it down slowly and the rubber band stretches out by some amount x, let's say. And here it's not moving. So it starts not moving because you're holding it in your hand, and you lower it slowly and it ends not moving. And the goal is to figure out how far does the elastic band stretch before it can support the mass at the end. All right, so in this particular circumstance, what's appropriate is to draw the forces that are exerted on the mass. You have the weight, the gravitational force, equal to mg, pulling the mass down, and you have the spring force pulling the mass up. And of course, the spring force in magnitude is equal to k times x. That's the thing about elastic forces. The force is proportional to the stretch. So if this thing is hanging in equilibrium and at rest, then its acceleration is 0. And using the ideas from the last chapter, these forces, this one and this one, have to be equal to each other. So k times x, the elastic force up, has to equal m times g, the gravitational force down. And that would allow you to figure out how much the spring stretches. You have to do the weight divided by k. I'm not going to do the whole thing here because I want to leave something for you to do. But you have the mass, 250 grams, and you have g, 9.8 meter per second squared, and you have k, 0.5 newtons per centimeter. But don't make the rookie mistake, as I call it. If you're going to do this, you're going to need to get the mass into kilograms, because to use these energy and force formulas, you have to use SI units. So that would mean the mass is equal to 0.250 kilograms. You have to divide by 1,000. And then the spring constant also, you see how it's newtons per centimeter? We're going to need that in newtons per meter, because that's the SI unit of the spring constant. And if you did that, you end up with 50 newtons per meter. So this screen's getting a little cluttered, but the long and short of it is, if you plug m in, got to have kilograms, g in is 9.8, and k in, got to have newtons per meter, even if it's in newtons per centimeter, you end up with something like 0.05 meters, which is the same as 5 centimeters. So if you were to let the mass go, not let it go, but lower it slowly, so that it comes to a rest and hangs at equilibrium at the end of the rubber bands, it would hang at equilibrium 5 centimeters below the point where this rubber band wasn't stretched. But that's not really what I want to do in this, because that's essentially what you did in lab. You added the water slowly and let it come down slowly so that the mass always hung at rest. What I'd really like to find out is what happens if I just let it go abruptly. So I'm thinking of a circumstance like this. So put the mass, I'm not going to draw the spring anymore, on the end, but it's not stretched. And then, instead of lowering it slowly, you just let her rip and let it fall. So now it goes down a distance not equal to x, because see what would happen if you let it go quickly, then it would end up overshooting that equilibrium spot and bounce up and down at the end. So what I'm thinking of is something where you put the mass on the end of the spring and you simply let it go. As the mass falls down, gravity pulls down, spring pulls up, it'll go right past the 5 centimeter mark, and maybe we want to know at 6 centimeters how fast is it going here, because it's not going to be going 0 meters per second because it's going to overshoot. So there's a number of things I'd really like to figure out here. What I'd like to figure out is over the distance that the mass fell, so again this 6 centimeters, over that distance I'd like to figure out how much work was done on it by gravity. And remember, work is an energy exchange, a transaction. So basically I'd like to figure out how much energy does gravity give the mass or take from the mass over the 6 centimeters that it falls. Now I know we found out that it would hang at equilibrium at 5 centimeters, but that's only if you lower it slowly by yourself. If you just let it go, it's going to blow right past that 5 centimeter mark and go further down and oscillate up and down. So over that same 6 centimeters, I'd like to figure out how much work was done on the mass by the spring. So again, asking for work, it's an energy exchange. I'd like to figure out how much energy does the spring give or take from the mass over this 6 centimeter fall. And lastly, because I didn't lower it slowly, I just let it go, we can use the work kinetic energy theorem to figure out how fast the mass would be moving if it fell 6 centimeters, while gravity pulled it down and the spring pulled it up. So let's give that a whirl. Let's take it one step at a time. Tell me what you think about the work done on the mass by gravity. Well, you can't really tell me, but I'd like you to take a minute and think about it out loud. Specifically, do you think gravity gave energy to the mass, or do you think gravity took energy from the mass? So in other words, is this work done by gravity, is it positive or is it negative? Now remember, this doesn't mean direction anymore. For work or energy exchanges, if a work is plus, it means the force gave the object some energy, and if a work comes out negative, it means the force took energy from the mass. So what do you think about gravity? Do you think gravity adds energy to the mass as it falls, or takes energy from the mass as it falls? Well, there's another little hint that you can do. You can compare the directions of these forces. So the force of gravity is down. The force of gravity, by the way, is equal to the mass's weight, mg, because remember, weight is the force that gravity exerts on a mass. And the direction the thing moves is also down. So when the force is down and the displacement is down, and when the force is constant, we can use the idea that work is equal to a force times the distance. By the way, I put that in quotes because you always have to do some thinking if you're going to use the force times distance method of calculating work, because you have to use the force that's aligned with the distance, and you have to make it plus or minus depending on whether these are parallel or anti-parallel. I made an audio commentary about that, and it's pretty well explained in the book. So the gravitational force is constant, and it's lined up perfectly with the displacement, and they're both in the same direction, so the work is definitely plus. And in this case, the work done by gravity on that mass would be equal to the force times the distance. And they're lined up, so it's plus. So you would have to plug in the mass, but again, got to do it in kilograms, and G, 9.8, or for the sake of argument, you could simply use 10 meters per second squared, because it's close enough. And then for D, you would plug in the displacement, the distance the mass falls, 6 centimeters, but again, you're going to want that in meters. So if I were plugging numbers in this, I would have to take 0.25 kilograms. I'm simply going to use 10 times 10 meters per second squared, and then times, again, the distance, but that's got to be in meters. So you got to do 0.25 times 10 times 0.6. What do you get if you do that? I find that the work done by gravity, the energy added to the mass, is equal to 0.15 joules. You get the same thing? There is, however, an entirely different way to look at all of this, and it's a way that involves using potential energy. Let me try to explain that way of doing it. So, potential energy gives us a way to calculate work done by so-called conservative forces. So, when the mass is up here, and when the mass is down here, 6 centimeters lower, the gravitational potential energy is not the same. If you choose this to be the reference level, then here the mass has some potential energy. Has potential energy, which is equal to m times g times h. And the height is d, because it's that high above the reference level. And here the potential energy is equal to 0, because the mass is at the reference level. So the way you can connect this up with work is as follows. When the mass is up here above the reference level, it has an amount of potential energy which is equal to, notice it's the same calculation as we just went through with work, force times distance. So when the mass is up here, it has 0.15 joules of potential energy, and when the mass is down here, it doesn't have any potential energy, at least as far as gravity is concerned. So it means that the work done by gravity, the energy that gravity is willing to give this mass, is the initial potential energy. So the thing about potential energy is, in a sense, it's stored energy. When the mass is up here before it falls down, it has some gravitational potential energy. But what that really means is that's the amount of energy that gravity is going to give the mass between the starting point and the ending point. So in either way, we can find the work done by gravity. It's 0.15 joules. That's the amount of energy that gravity adds to the mass over the distance that it falls, 0.6 centimeters. Okay, let's take the next part. How much work is done on the mass by the spring? Well, we might think that we can use the force times distance way. So could I do the work done on this spring, could I say the work done by the spring on the mass is equal to some force times some distance? Because that seems to be the go-to formula for work. But the sad truth is you can't do this. And the reason you can't do it for springs is because the force is not constant. As we learned in lab, the force increases the more the spring is stretched. And this force times distance way of calculating work only works when the force is constant. So we're going to have to come up with another way of figuring out the work done on the mass by the spring, the amount of energy that the spring is going to give to or take from the mass. Well, let's first of all decide whether or not you think that work will be positive or will it be negative. So is the work done by the spring, is it, like we were saying before, is it plus or is it minus? Take a minute and think about it. To give you a little bit of a hint, we can do the same thing we did before. Which way does the mass move? Down. And which way does the spring pull? Up. So the force exerted on the mass by the spring is up, but the distance the mass moves is down. That's the hallmark for negative work, when the force and the distance are anti-parallel. So in this case, the work done by the spring is going to be negative. And since we can't use the force times distance way of calculating work, we're going to have to use the potential energy way of calculating work. So let's stop and think about it. Draw a before and after picture like we had before. So here's the spring again, mass hanging on the end of the spring, no stretch. And then later, the spring is stretched out by this amount that we're calling D. So here, there's no spring potential energy because there's no stretch, there's no potential energy. Now, it's true that there was gravitational potential energy, but we're not considering that anymore because we're talking specifically about the spring. But here, there is some potential energy because the spring is stretched. The potential energy here is 1/2 kx squared. So we have enough to evaluate the potential energy here. We're going to take 1/2. We're going to multiply it by k, but k we got to get, by the way, in newtons per meter. So it would be 1/2 times 50 newtons per meter. And then we got to multiply it by the distance squared, but we got to get that in meters. So I got 1/2 times 50 times 0.06 squared. You can work that out as well as me, but I find that this potential energy of the spring here is 0.090 joules. Do you agree? So, what does that mean about the work done by the spring? Well, did the spring give or take energy from the mass? I feel that it took energy from the mass. It took energy from the mass because as the mass was moving down, the spring was pulling up. Another way to look at it is the mass gave some energy to the spring because the spring wasn't stretched here, so it wasn't storing any potential energy, but the spring is stretched here. So the energy that went into the spring, this 0.090 joules, came from the mass. So the work done by the spring is equal to minus 0.090 joules. So you have to do two things when you're calculating or analyzing situations using the work kinetic energy theorem. You have to figure out whether or not work is plus or minus by comparing the directions of the forces. And then you can calculate the work in a variety of ways. That's probably a little confusing. For gravity, you can use mgh to calculate the work, force times distance. Or you can use the potential energy trick, which is actually better and more reliable, because potential energy tells you directly how much energy goes into or comes out of these infinite sources or sinks of energy. So gravitational potential energy, the interaction between a mass and Earth, is like an infinite source of energy that a mass can draw from, or an infinite deep sink that a mass could put energy into. So springs also are that way. Since they can store energy, you can put energy into a spring or you can take energy out of a spring. That's what potential energy is for you. Maybe a spring is not as infinite a source as gravity is, but nevertheless it works. So last but not least, how fast is the mass moving when it gets down to this 0.6 centimeter mark again? Well, here you can use the work kinetic energy theorem. So the work kinetic energy theorem simply states that the total work done on an object is equal to the object's change in kinetic energy. So the total work, if you account for all of the energy that an object gets or receives over an interval of time, that energy can only go in to changing the kinetic energy of the mass. So we can figure out the total work in this case, because the total work in this case was the 0.15 joules that the mass got from gravity minus the 0.09 joules the mass had to give to the spring. So the total work comes out to be 0.06 joules. And notice that it's plus, because the mass gets from gravity more than it loses to the spring. So since the total work is plus, I know that the kinetic energy at the end has to be greater than the kinetic energy at the beginning. Because kinetic energy, I guess you could view that as its bank account. So it got 0.15 joules from gravity. It gave 0.09 joules to the spring. So overall, it ended up getting the net effect of these two transactions. It ends up getting 0.06 joules. So that has to go into the mass's kinetic energy bank account. Well, the thing is, the mass starts with no kinetic energy because it starts with no velocity. You released it from rest. So the change in kinetic energy, which is always the final kinetic energy minus the initial kinetic energy, that's always the way we do that. But the initial in this particular case turns out to be 0. So the final kinetic energy, which has to equal 1/2 times mv squared, has to equal the total work, 0.06 joules. So I'm going to have to leave this last little bit to you because I haven't conserved enough space on the screen, but you have enough here to solve. You can solve for the velocity. So you'd plug the mass in, 0.25 kilograms, and you got the 0.06 over here. So I'll give you the answer, and then you should verify that you get it. It's going to be a square root involved in here, but give it a try and see if you can't get 0.69 meters per second. So to wrap all this up, we found that if we release the mass slowly and let it go slowly to its equilibrium spot, then it would only go down 5 centimeters where it would rest. But if you just let the mass go at the top, it'll overshoot that 5 centimeter part, and it'll be moving when it goes down even further. In this case, we just picked 6 centimeters. There is a slight difference between these two things from an energy perspective that deserves maybe to be mentioned. So when you do the mass slowly and when you let the mass go quickly, you get two different outcomes. What's the difference? Well, if you lower the mass slowly, okay, it stops with v equals 0 at 5 centimeters. But if you just let the mass go, then it overshoots and it has some velocity which is 0.69 meters per second at 6 centimeters. So what's the difference between these two things from an energy perspective? If you just let the mass go, then there's only two things that do work. There's gravity, which adds energy to the mass, and the spring, which takes energy from the mass. And the mathematics shows that the balance is in the mass's favor, in the sense that, or in gravity's favor, in that gravity gave more energy to the mass than the spring took away. But if you lower it slowly, there's three things doing work. There's gravity, which adds energy to the mass. There's the spring, which takes energy from the mass. But there's also you. You have to lower the mass slowly in order to have it stop at 5 centimeters. And that lowering slowly would require an upward force along with the downward displacement, so you would end up doing negative work. And it would balance out. So if you lower it just slowly so that it's got no kinetic energy at the bottom, and it had no kinetic energy at the top, then the amount of work you do is equal to that 0.06 joules. You had to take away that little bit of extra energy. Well, anyways, I hope this long example didn't get too cluttered. My point of doing a long example with a number of parts is that it allows me to describe more of the concepts of work and energy, and also gives you small examples that you can apply to the problems that you work on at the end of the chapter.